Okay. So we discussed the basic ideas of how a star form, and of course I told you that you have all this dust that collapses and create the star. And what is important is that then you have nuclei that are brought together to the point that you have the beginning of nuclear reactions. But this doesn't tell us so much about what the star is made of. For instance, I told you that a star can be of first generation, or it can be also the product of some other previous explosions, some other stars that died before. So in this death, the star is spreading around metals, materials such that the elements that compose these materials are more heavy. But so how can we know how a very distant star is composed? Well, fortunately, we have quantum mechanics for that. Remember the fact that we studied in quantum mechanics that one of the magic of quantum mechanics is that in one equation is able to explain suddenly why you have all the different elements. So each atom of a different element is constituted by a nucleus with different orbitals. And the shape of these orbitals is dictated by the equations of quantum mechanics. And in particular, the equation of quantum mechanics tells you what is the difference in energy of an electron that stays in one orbit and an electron that stays in the other orbits. We saw that the characteristic of quantum mechanics is that there are jumps between different orbits. And so this means in particular that each atom have a signature that is given by all the possible jumps that can happen within that particular atom. So of course, in the so this means that if you receive lights that is produced by electrons that are jumping within an atom, you will see some very characteristic lines of light, lines of different colors, and each of these lines will be associated with a particular jump. Sorry, I was talking about lines. I throw this to you as if it was obvious. So of course, what you see would be just light with any particular color. But you know that when you have when you have light that travels to you, this can be constituted of photons with different wavelengths. I hope you have seen at school, this was one of the basic results by Newton. There is the famous Newton disk. It's something very nice you can do at home. You take a disk and you color it with different, like with pieces, each one with a different color, like the different colors of the rainbow. And then you make the disk turning, and you see the disk being white. Okay. So similarly, okay, we can receive generically some light, not of a specific color, but there could be different. We have seen that there could be at the same time light of a different wavelength that is traveling together. But for each atom, these wavelengths, the different energy of the photons that compose this flux of photons are very specific. And how do we know how to which one they are? Well, there is a very nice phenomenon in optics that is that when you create a a slit. So like you have a screen. If you have a screen with just not a hole, but sorry. Maybe they were interested in this. They want to know what stars are made of. So they should, it's nice. So, okay. So you have probably seen that if you have some light that goes through some slit, then on the other side, the light opens up in the different component, so the different colors. So you see something like a rainbow, basically. So this is the principle at the base of spectrography. So most of the time, actually, astronomers, they don't look at stars just watching directly the light that comes from them, but they use a spectrographer, that is an instrument that when lights arrive splits the different components, so the light with different wavelengths, and in general, so you would see these different colors, let's say, being distributed evenly. But if you're looking something that is made of a very specific element, then instead of seeing just like a rainbow in which all the colors shift from one to the other, you will see just one line, then another line, then another line, then another line. And these lines are the jumps from quantum mechanics. So studying the lines that corresponds to the studying the lines that appears from the light that comes from stars, it's possible to derive what the stars are made of. And in particular, something that was discovered only, well, it's basically 100 years ago, is the fact that most of stars are mostly composed by hydrogen and helium. So hydrogen and helium are the simplest possible elements. This discovery was made by Cecilia Payne. Another case in which people didn't pay too much attention to what she was doing, except that she turned out to be right. And it's quite astonishing the fact that she proposed this idea as part of her PhD thesis. Yeah, I saw your face. Yes, sometimes, actually, also some of the discoveries that were made for quantum mechanics, they were just the PhD thesis of those young people. At the time it was possible. Sometimes I really wish for you also that you made this kind of discovery. I think it's still possible, so I wish you the best that you can make a discovery like this during your studies. Maybe you don't have even to wait for your PhD even before. So Cecilia Payne was the person who first discovered this, and actually the women were really the people, the part of humanity that helped the most to understand what stars are made of. So here you see two pictures. The pictures below, it's from what was called, ironically again, the Pickering harem. So Pickering was the director of the Harvard Observatory, and was a bit derided. I mean, his colleagues were making fun of him because he was hiring a lot of women. But these women, with their patience and their precision, were able to make catalogs of the objects in the sky. I mean, and as you see, the person who became later the chief of this group in the observatory, that is, oh my God, I'm missing her name. Well, in every case, was the person who alone made the larger catalog of stars. So you see here in 1887, there was the development for the first time of photography. So photography before was not an instrument for astronomy. In the moment in which it became available, there were more than 20,000 plates of pictures of objects taken of objects in the sky. And so some of these photographic plates were reporting, in fact, it was not just directly the picture of the object, but they were actually spectrographic photographies, so showing the different lines associated with the objects. So these women were able to find a way to create a catalog and associate different categories for different kind of stars, presenting different spectrographic properties. So this is about how do we know what stars are made of, and the other question is how do we know how far are the stars? Well, at the beginning, I saw you the picture at the very beginning in which we saw this picture of the universe with all the the solar system and all these stars around us. And I have already told you something before, because so you see here there is about 100,000 astronomical units. So this is halfway to our closest star, neighbor star. And so this means that the distance of the closest star is about 200,000 astronomical units. But in general, how do we know the distance? Well, the first thing you can do is to use a geometrical method. And here we can do a little, so this is a good experiment, especially for those that are in the back. So I want you to, like, you are seated, you are sitting, you take something in front of you. It could be, don't use the head of somebody else, use like, I don't know, a seat in front of you. And then look at what is the position of this object with respect, say, of the screens here, okay? And then try to do something like a movement like this, trying to understand, try to see, yeah, you're doing it right. So one possibility is that you do this like this, but the problem is that you have to do it, keeping it in the same position. Like, don't do this, okay? Just keep it right. Yeah, okay, do it, that's good. Or like, okay, you pose it. And the point is that you have to check how the apparent position of your reference object is shifting with respect to the background. So this is what is happening here. If you have a certain star, and if you see that its apparent position, it's moving with respect to the fixed stars that are simply the stars that are even more far away, then by studying this shift of position, you can derive how far is that object, that star. So you're assuming that the very distant stars are at an infinite distance. And when I talk about infinite, it just means that it's so much bigger that I don't care how much bigger it is. It's just big, 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 too much, uncomparable. So it's an infinite distance far away. So they appear as fixed. I don't see any movement. and I can study this this movement, this apparent movement of the stars. Notice that so using this method is called studying the parallax. The parallax is this apparent movement of the object with respect to the background. And this was something that was known since antiquity. It's something that is discussed even by Greek astronomers, except that Greek astronomers used it to say that all the stars were fixed at a fixed distance because they couldn't see any parallax. Sorry, I made this wrong. So you see that to exploit this technique, we were moving our heads. So what is the equivalent for us, for astronomers, of moving the head? Is the fact that the Earth from which we are observing is at different positions with respect to the sun. So sometimes it's one side, sometimes it's on the other side. So of course, if you look at the stars far away, when you're observing here, you see different position than observing here. So if you keep on observing the same object during a wall here, then you can reconstruct the shift, the wall shift with respect to the background, and therefore you can reconstruct the distance. Except that in the Greek world, the Greek astronomers were seeing no parallax at all. And this was an argument to say that the Earth is not moving with respect to the fixed star, except that this was happening simply because they were not using telescopes. They were not getting the help of instruments, and all they could see was just through their eyes. So in the moment in which telescopes became available, and also using photographic plates and so on, so this became possible. And so we started to understand what was the distance of stars. Now, this is a technique that works well. It works well in particular, it works well for stars that are sufficiently close to us. The problem is that in the moment in which you wanted to study stars that are more far away, you need to use some other technique. So now I wanted to introduce to you something that is, so I was talking about parallax, and we have a new astronomical unit that is called the parsec, that is the distance under which the movement of the stars is seen as being just 1 degree in the sky. So, okay, so this is one more way in which, so you use the parallax and you use the unit of movement to talk about the distance of the stars. Again, as I was saying, this technique is available only for stars that are close to us. So we need something else to talk about stars that are even more far away. So as I was mentioning before, instead of talking about parsec, parsec is a good unit as long as you are looking at things within our galaxy. But if you wanted to look at things out of our galaxy, well, there could be better units to use, better methods of measurement. So this brings me to the next character for the last, one of the last characters for today. That is Henrietta Leavitt, who was also a member of the group of astronomers in the Pickering Harem. And what, as her colleagues, Henrietta was studying the characteristics of stars, looking at the spectrum, studying their luminosity, and so on. among the stars, so one of the things that was understood studying stars was that stars were not just regular objects, always shining with the same luminosity, always shining with the same colors, and so on. They could evolve. So there could be in particular variable stars, and there are different classifications, different possible variable stars. So what Leavitt noticed was that there was a specific class of variable stars called Cepheids, and Cepheids is just associated to the constellation in which they were first discovered. So those were variable stars. They were like pulsating. That means that they were changing size and temperature and brightness with a very precise regularity. So that it was very, very regular. So, and they were doing this. So every time you were finding a star of this kind, this star was presenting exactly the same kind of pulsation. But so this means that these kind of stars can be used as a standard candle. So this is something that is very important in astronomy, is the fact that you need to know what are the properties of some particular objects. That is, we call it a standard candle. It's standard, you understand the candle, because it's something that you measure in terms of its brightness, how much light is shining towards you. So once you use the characteristic of, you know the characteristic of this particular object, you can also check how this object presents itself at a different distance. And therefore, because you know what is the pulsating period, you know what is the characteristic luminosity, then you can infer at which distance this object is. So this is an amazing technique that is due to Leavitt's law for these pulsating Cepheids stars. And this opened the way to understand that the universe is larger than what we thought. So we started with a universe that is just our solar system. Then we understood that there are other stars. And now we know that these other stars also have planetary systems. In most of the case, they have planetary systems around them. But there was a moment, so to this point, actually till 1924, it was not understood that we are in a galaxy and that there are other galaxies. So before, we thought that there are stars all around, possibly forming a galaxy, but that's it, that's all, okay? Actually, the first person who think about a galaxy that is kind of an island universe made of a lot of planetary systems, it was Laplace. So this was an old idea from the 18th century. But there was this enormous discovery in the moment in which we were able to have a new technique to compute distances, also very far away distances. This opened the way to understand that the universe is much larger than what we thought before. And what happened was that the astronomer Hubble saw in another galaxy. Now we know that is another galaxy. At the time, why I put in the title of this lesson, little clouds, where people were observing a lot of little clouds, you know, like little things that look at like I don't know, just like some cotton, something fluffy. And I mean, I don't know if you had the chance to see this kind of things on a telescope, but what you see with your eyes is really just this undistinguished, the fluffy clouds. So by observing one of them, Hubble realized that one of the objects, one of the little dots that was making up the cloud was in fact a Cepheid, because it was showing exactly the kind of pulsation that is characteristic of this variable object. And he was able to derive that this object was very, very far away from us. And therefore, the whole cloud should have been a separate system with respect to where we are, with a lot of space between us and that. And this other system, now we know, it's Andromeda. It's the closest galaxy that we see, that we have in our neighbor. And actually, you can see it with even with the binoculars. It's very beautiful to see. But what you will see, in fact, is just a little cloud. But it's something that even yourself, if you have just a good binocular instrument, you can see it. And yeah, and so here there is a picture of Andromeda, and here is a picture of what we see now with our instruments. So each of these little cloud is one galaxy far away from us. So the universe is in fact full of galaxies. There are as many stars in our galaxy as there are galaxies out there. To understand better all these things, we need to understand more about cosmology, to understand how old is the universe, how old could be the first star, for instance. And in order to understand galaxies, we needed to discuss black holes. That is part of the story of what happens when a star dies and collapses. So that's everything I wanted to tell you for today. And next week, we start talking about cosmology.
Hi,
Yeah.
do you potentially know when we have our marks back from the first midterm?
Yeah, it could be even everybody. So we had the last makeup today for the students who were ill with accommodations during the midterm. So by the beginning of next week, you will have also the result of the midterm. And I'm not gonna share with you all the answers, but you are very welcome to sign up for the office hour, and we can discuss your answers together.
I think the last day to drop a course is the 14th.
Okay.
So I don't know if
You want